Hey, before I talk into the meat of this video, I'd just like to mention that I don't need the pedal I'm building, and I'd like to pass it along to someone watching this. If you want a chance to receive it, just hit my email, listed below, with evidence of recent charitable activity like volunteering or donation, obviously sanitized of sensitive information. Once I've got a good handful of applicants, I'll randomly choose one, maybe even on stream, and if you're selected, I'll contact you to let you know, and as long as you can cover the cost of shipping, it's yours. I will exercise some discretion in terms of accepting applicants, but rest assured that no charity is too small. $5 from someone with almost nothing means more than $100 from someone who's got almost everything. I'll take this preface down once the pedal is accounted for, so if you're seeing this, you still have a chance to get in. Hi, I'm Zach, the Gabahan Saturation Sound, and this is a build walkthrough of my Teez DIY packing board. It's a boost-only mid-range shaper based on T-section filters, which I've seen used in some wah pedal topologies. We'll begin with the power supply. The first component is this diode, marked on the board as D1. I recommend using a 1N5817, which is a Schottky diode with a very low forward voltage drop. So you can just use it directly in line with the 9-volt input as your reverse polarity protection. From there, we'll use this 4.7 ohm resistor, which contributes to the ripple filtering in conjunction with the main filter cap. Said filter cap is this beefy 100 microfarad capacitor. It's an electrolytic capacitor, which means that it has a set polarity, so take care when populating the component. The positive lead on the component should be a little bit longer, and the negative lead is both shorter and should be marked with a gray stripe on the capacitor body. On the board, the silk screen should denote a positive terminal, which is also marked with a square pad. Because we're going to be working with op-amps, we do need a bias reference voltage, which will derive with a voltage divider created with these two 10K resistors. Now the middle node between those, that resistive voltage divider, will feed this 47 microfarad electrolytic capacitor. Again, take care of polarity when installing the part. Once your parts are populated, bend over and crimp your leads to give them some mechanical support to the board itself. Once your leads are bent over and crimped, take out your trusty little side cutters and trim off the excess from the leads. I like to go just about to the edge of the pad. Now I'm speeding up this section a little bit because I didn't realize that I was trying to solder with too low of a temperature. Once I got that rectified, we'll do it at normal speed. So, when soldering, It's a good idea to tin your iron with a little bit of excess solder, which helps with the thermal transfer. Then use your iron to heat the joint between the pad and the component lead. Then flow a little bit of solder into the joint itself once the parts are heated up properly. Ended up having a little bit of excess on one of my filter caps from the little mistake that I made with the temperature juggling. But that's easy to fix. Next we'll be installing a socket for the op-amp. I like to socket these so I don't have to apply any significant heat to the component itself. In my imagination it helps with the health and reliability of the circuit, but it might not be necessary. When installing your socket or the op-amp, take care that they are oriented correctly. There is a notch on the silk screen which indicates the orientation of the socket, and the pin 1 hole is denoted with a square pad. Next we get to the input of the circuit as well as the first buffer stage. The first component that I'm populating is this 1 mega ohm resistor, which serves as a pull-down resistor. This, in conjunction with the good bypass switch wiring, helps minimize switch popping by bleeding off and preventing the buildup of charge on the input-facing side of the input coupling cap, which in this case is this 1 microfarad capacitor. You'll note that this build features far fewer of these than the other DIY pack-in boards. Next we need a second 1 mega ohm resistor, which will be delivering the bias reference voltage to the op-amp. Now a bias voltage is important because the op-amp can only reproduce voltages between the upper and lower limits of its power supply, in this case 0 and 9 volts. Your input signal will probably contain negative voltages, which the op-amp cannot reproduce. So to get around this, the bias voltage shifts the operating point up from 0 to about 4.5 volts, giving it some room to swing up and down around that point. Next we'll be getting into the passive EQ circuit itself. So, normally I like to populate components as the signal would see them, and the next component would be this B250K potentiometer. But instead, because that's going to get in the way, I'm just going to populate the main filter networks first. Now, describing what each component does in these sections would be pretty boring, so I'll describe the groups of components in blocks. The first block we'll look at is this upper section. It needs this 22K resistor in series with the filters to equalize the gain with the lower block. Said filters are a high-pass filter and low-pass filter in parallel with each other. Because the signal has valid pass through both the high pass and low pass filters, most of the input signal passes through except for frequencies around the cutoff points of the filters. This is called a notch or band reject filter if you want to sound like a Poindexter. You'll also notice that I realized that I had the wrong values of capacitors, so I had to make a quick run to the shop to get the correct value. These filters are built entirely out of 10K resistors and 22 nanofarad capacitors. These values can be tweaked to change the frequency response of the EQ circuit, but the maths behind how various changes would affect that are somewhat complicated. So you would really have to experiment around to find something that works for you. Now, this lower block, as opposed to the upper block, has both of the filters configured in series. This means that the input signal would have to pass through both filters before reaching the output. Because both the extreme high frequencies and the low frequencies are chopped off, this would make it a bandpass or bell filter. Much like with the upper filter block, the components are all based around 10K resistors and 22 nanofarad capacitors, so that the bell boost and the V boost, as can be called, should be roughly symmetrical. Now, there are some quirks in the overall frequency response of these filter topologies, but we'll get to that when we get to the output amplifier. I'll include some notes on potential modifications in the bill of materials document listed below. Now we'll get onto the potentiometer finally. First, cut some lengths of some hookup wire. You only need a few inches to make the connections. Next, break the ends of the insulation with a pair of wire strippers. In other builds, I've considered chopping off the ends of the pot shaft, but because I'm going to be using a very large knob, I might not have to. Then, take that broken end of insulation and twist and pull it off, which will braid up all the strands of the hookup wire in one smooth motion. Then simply heat up those exposed strands and flow a little bit of solder into the wire. To connect the wires to the pots, take one of your tinned ends and bend it into a little hook. Feed that hook through the lugs on the potentiometer, crimp it shut, then heat up the lug in the wire and flow some solder into the joint. And repeat for the subsequent lugs. Because this is a fairly large board, and we want to put it into a fairly small enclosure, the board is going to have to sit over the pot itself, which means we will need some insulation to keep the conductive pot body away from the exposed contacts on the back of the board. I'll just use the bag that the pot was sold to me in. Simply position the bag on the back of the board, mark the spot that the wires are going to have to be passed through, mark your hole, and slice it open. When connecting the pot to the board, the pot lugs are typically numbered as 1, 2, and 3, which corresponds to the holes on the board, which unfortunately I forgot to number on this silkscreen revision as 1, 2, and 3. But the pin 1 hole is marked with a square pad, as is my convention, and they simply count across as you would expect. So when looking at the top of the board, it's 1, 2, and 3, as 1 is on the left, and when looking from the underside, it goes 3, 2, 1, as the 1 is on the right. Now, the way this pot works is actually borrowed somewhat from the Big Muff tone stack. On the Big Muff, it uses a 100K potentiometer to effectively pan between a high-pass and a low-pass signal, giving you your brightening and darkening effect. In this case, it's panning between the previously discussed bandpass and band reject filters. Oh, I guess I'm a Poindexter. Thus giving you your bell boost or your V-notch boost when we get to the final amplifier stage. Speaking of, these components are used to set the gain of the final amplifier. Now, op-amp gain is based on negative feedback. The op-amp will try to equalize the voltage seen at both its inverting and non-inverting inputs. If there is a voltage divider of some sort between the output and the inverting input, the output will have to work harder to make the inverting input see the same voltage as the input at the non-inverting terminal. In this case, the top part of that voltage divider is this 56K resistor that connects the output terminal to the inverting input terminal. However, there is a quirk in the filter networks that causes a weird treble gain boost. So to compensate for that, we'll be using this 3.3 nanofarad capacitor, which will create a bypass path around the 56K resistor for upper treble frequencies to pass through. We don't need that much attenuation, so we'll be using this 220k resistor, marked on the board as M22, which will be seen in parallel with the 56k resistor, thus shrinking the top part of that voltage divider a little bit for treble frequencies. The bottom part of this voltage divider is presented by this 820 ohm resistor. So yeah, there is a fair bit of gain in this output amplifier. Now, another quirk that the filter topology provides is a surprisingly huge bass boost. So I'll be compensating for that with this capacitor down here. This capacitor serves two purposes. The first is that it blocks the division of the DC operating point. So it will always be operating around 4.5 volts. Additionally, it is a fairly small capacitor at only 220 nanofarads. So the absolute lowest frequencies, which are somehow passing through the filter network, don't have as much gain applied to them as the rest of the signal. Finally, we get to the output of the circuit. This 1K resistor here is a bit of a short circuit protection for the final op-amp. I never really find myself really needing one of these, but I guess it is best practice to include. This here is the output coupling cap. It is a 1 microfarad capacitor and serves to block the DC bias voltage from whatever happens to be following your effect. And this final 1 mega ohm resistor here is another pull-down resistor, which helps minimize switch popping by bleeding off any charge that builds up on the output-facing side of the output coupling cap. Now that all the soldering is complete, we can install the op-amp IC. In this case, I'll be using one of these little TL072s. To ensure that it's installed correctly, take note of where the pin 1 indicator is. It should be a little dot on the IC body right next to pin 1. On the silk screen and on the socket, the side with the notch cutout is the side that indicates pin 1 and pin 8 on the left and right sides respectively. When you receive the op-amp, the legs are going to be splayed out a little bit. Simply place the legs on a flat surface and gently bend them inwards so they are close to parallel. Then simply place it on top of the socket and gently press it into place. I said gently press it into place. There we go. One of the legs tried to kick out on me. Now that we're finished, all that's left is enclosure prep and assembly. I've already shown how to do this in the Glass Booster DIY project, so I'll just add a card pointing to that video here. Note that the Teez board is larger than the Glass Booster board. So depending on how you lay the board inside the enclosure, you might have to move some parts around.